Okay, very good. So it seems that everybody is here. Philip, is it okay? Can we start? Or?
Yes.
Okay, very good. So it's a great pleasure to have everybody here. So this is the last lecture of Jan-Philipp Solovej, and as usual, if you have any questions, feel free to ask him or keep it for the end of this talk. Please, Jan-Philipp.
Yeah, thanks a lot. So this time I will actually be giving a lecture not on slides, but by writing on the iPad. But let me just remind you of what it is that I'd like to discuss in this last lecture. So in the lecture we just had on Tuesday, I was discussing this, what I call the Fermi formula for the occupation number of angular momenta in a real quantum net. Now, so this is a discussion really about the bulk of electrons. So most of the electrons in a very large atom, they are with angular momentum to the 1/3. But I have also tried to emphasize that much of what we're really interested in is chemistry, and much of the periodicity and the universality would be happening sort of for the very last electrons, the ones that are where when you remove, say, one electron from an atom to understand the ionization energy, that it is a bounded quantity, or to understand that the radius where the last electron is something that actually behaves in a way that where it's bounded independently of Z. As I said, we still think that there's some periodic behavior for large Z for the radius, but it's bounded above and below independently of Z. And that is the statement that I made here, that if we calculate the radius either in Hartree-Fock or in reduced Hartree-Fock theory, and take the limit Z going to infinity, well, we don't expect the limit to exist, so we do lim int and lim z. But both of these limits will exist, and they have the same asymptotic form when I remove many electrons. So I first let Z go to infinity, so I'm really then talking about an infinitely big atom, and I'm starting to remove electrons. And I claim that when I start removing many electrons, then the radius will decay with some explicit constant n to the minus. So that is the result I'd like to prove to you today, and I'd like to prove it in the reduced Hartree-Fock model simply because it is a little easy. And I will do it by writing on slides. And actually, the thing I would like to do is a slightly different statement, but I'll try to explain the relation. And I also would like to prove the ionization conjecture in this reduced Hartree-Fock model, meaning that the critical number of electrons that you can bind is the Z plus a constant. So I will be assuming, I will consider the reduced Hartree-Fock model, and I will assume that we have a minimizer gamma with a trace of gamma greater than or equal to Z. So I will look at both the neutral atom and the largest possible atom. So I will end up actually getting a bound on what this trace can be, that it cannot be arbitrarily big, because I'm assuming that there is a limit. So that is what I'd like to do. And here's the claim that I would like to show. I'd like to show that there exists an epsilon bigger than 0, a constant bigger than 0, and a radius also bigger than 0, and they are all independent of Z, such that I have the following statement, that the integral, the number of particles that I have in this rho hf, or I can also just write it as rho gamma actually, that the integral of rho gamma minus the same integral for the Thomas Fermi And here I mean the neutral Thomas family. So rho z Tf is the neutral Tf. We know that that's the largest you can have, the largest number of particles you can have. I mean the integral of this is rho z Tf is equal to z. I don't know why this is not writing so well. Okay. So I claim that this is bounded by C0 r to the minus 3, 1 minus epsilon for r less than or equal to r0. So the point is that I claim that I have a control on the number of electrons inside a ball, its comparison to the Rho-Thomas family theory, all the way out to a radius r, which is independent. Okay. Now you may ask, is this even a good estimate? But let me just say that an equivalent is, so I will call this estimate here, I will call star, and I will spend most of the time today proving this estimate. Equivalently, if I introduce what I would call the screen nuclear charge, so let me say it for this. If I look at the screen nuclear charge, so this is something I will call nu of r, and this is z minus the electrons that are inside the ball of radius r. And here I wrote it without decorating it by whether it was reduced Hartley Fock or it was Thomas Fermi. So you can do this in all the models. So in fact, what the claim that I have before, I can subtract the z on those from both sides, and I would be getting that equivalently I have the statement that nu gamma of r minus nu Tf of r is less than or equal to C0 r to the minus 3, 1 minus epsilon, when r is less than or equal to. It's just an equivalent statement, and let me call that 1 star star. And actually, let me just pull this over also on the next slide, so you can, oops, I don't want to move it, I want to copy it and paste it here. So I want to estimate how big is actually this nu Tf of r. So recall that one of the things we saw about rho Tf, so one of the things we saw about this rho Tf density is that it's less than or equal to, I think I called it constant d, maybe a universal constant times x to the minus 6. So that means that the nu Tf of r, that is equal to z minus x less than or equal to r rho Tf of x dx. But since the total integral of rho is z, this is the same as integrating rho outside. And since it behaves like dx to the minus 6, this is actually even the sharp behavior. But we certainly have the bound that this is bounded by r to the minus 3, but this is actually the correct asymptotic form for large r. Well, it's not d here, it's some other constant. It's not the same d as some 4 pi. But in any case, so the nu Tf of r behaves like r to the minus 3. So what we're showing up here is that the difference between these two is lower order than the leading term in UTF, which is of the form r to the minus 3. Okay, so in order to estimate this, I would I want to get into a semi-classical approximation. But I'm actually going to estimate things in using the electrostatic energy as a norm. So I will introduce the Coulomb norm. So in general, I mean, this is called Fc, and this is simply the self-energy, f of x, f bar of y, over x minus 1, dx. We know this is a positive quantity, so it defines a norm, and I mean, if you express it in Fourier transform, then you not get all the coefficients right. They will not be important, right? But this is equal to some coefficient within the Fourier transform of f squared p to the minus 2 dp. Right? So this is how we see that it is indeed a norm. And I will be estimating using this norm. Okay, so I will be doing a semi-classical estimate, and I'm doing everything for the reduced Hartree-Fock model, so let me just remind you what that looked like, right? So we have this reduced Hartree-Fock. I have the minimizer gamma, depends on z, so this was the trace of minus 1/2 Laplacian minus z over x, and then gamma, and then we had to add gamma. So, right, because that's exactly how I defined the Coulomb norm. It had the 1/2 in there and everything, so this is the term that we had there. And if you recall the way I did the estimate, when I did the semi-classical estimate, I actually rewrote this by smuggling in the Thomas Fermi density. So I rewrote this by saying this is the trace of minus 1/2 Laplacian minus z over x gamma. And then instead of writing the rho gamma Coulomb norm, I subtracted off here the Thomas Fermi. And now let me not put in the z all the time, and when I have the Thomas Fermi, I'm always, well, at least for a while now, talking about the neutral Thomas Fermi. So I added that in, but then of course I'm making a mistake, so I had to subtract off again from this the self-energy of the Thomas Fermi itself. So the Coulomb norm of that. And then there was also the cross term, and the cross term I wrote as the plus the integral of rho Tf involved with x inverse times rho gamma. Like that. And then I can take this and this last term here and including it up there, and then I get the mean field Thomas Fermi equation, so I get the trace of minus 1/2 Laplacian minus z over x gamma. Sorry, I wanted to now write it as the Thomas Fermi mean field, so it would become the phi Tf gamma plus minus rho Tf Coulomb norm, and then extra term here, rho gamma minus rho Tf. The Coulomb norm of the difference between the two. So that's an identity. Now, when I did something similar earlier on for the full quantum model, but then there was an error term. This was this that ended up being z to the 7/4, and that came because I had to estimate the exchange term. But here there is no exchange term, so here this is in fact just the line. But what is interesting is that we also have a similar upper bound. So, and this is the thing I did not really discuss in detail, the fact that there is an upper bound in terms of, you can use a gamma, which is a semi-classical approximation to the reduced Hartree-Fock minimizer, so that you can actually find that the trace of, that this E, Z, RHF of gamma is in fact also less than or equal to the trace of -1/2 Laplacian minus 5 Tf negative part minus rho Tf c squared. But that has an error term, and in what I'm discussing today, the only thing I care about is that the error term is lower order than 7/3. And then we say 1 minus eta or some eta positive. Okay, so this was enough. This is not so difficult to show. I didn't do it, I didn't have the time to do it, because you can write down, you can in fact use coherent states to write down an approximation for the negative spectral projection of this operator. That semi-classical expression would be an operator between 0 and 1, and you can plug it in as a trial state for the reduced Hartree-Fock minimizer, and you will get this with that error term after some actually not too complicated calculation. But now you see that, of course, this term here is always bigger than or equal to that term, because that is the smallest you can get. That's what you would get if you actually had the negative spectral projection for this operator. But the gamma is the minimizer of the reduced Hartree-Fock. In any case, this thing is bigger than that. So we actually have a lower bound. We have an upper bound on this quantity, which must mean where this thing is actually smaller than this, which means we must actually be getting an upper bound on that quantity. Right? So we must conclude that this Coulomb norm is less than the other. Because this is smaller than that, sorry, this is bigger than that, right? So therefore we would be able to continue an inequality here. Here we could have continued the inequality as a lower bound, and we could have written this thing instead of that. But since we know this is also an upper bound, it must mean that this term is less than. So in other words, we conclude that the rho gamma minus rho Tf in Coulomb norm is less than or equal to some constant z, and since this was the Coulomb norm squared that I had here, and so now I take the square root, so I get 7/6 instead of 7/3, 1 minus eta, where eta is some positive. So this is one thing I want to use to compare the integral of rho gamma and rho Tf. But that's not going to be enough. I need also to remember that I have control on the 5/3. Right? So recall that we also have that the integral of rho, maybe let me write it as norms again. We know that the rho gamma 5/3 norm, this came from the Victorian inequality, as well as the rho 5/3 norm of the Tf, well here you don't have to use the Victorian inequality based direct, but these 5/3 norms, they are also given by z, by some constant, z 7/3. But then since I'm calculating the norm, I have to put 3/5 here, and so this is equal to a constant z to the 7. So I have those two bounds. And now I claim that from these two bounds, I can control the difference of the integrals. And this is a little lemma, so let me put this little lemma here, and I'll move it, that says that if I have two densities, so if I have rho 1 and rho 2, I'm going to use the lemma several times, so I'm stating it more generally. If they satisfy that rho 1 in the 5/3 norm and rho 2 5/3 norm, if they are both less than or equal to A, some constant A, and their Coulomb norm is is less than or equal to, say, b, then the integral of rho1 minus rho2 in absolute value for x less than or equal to r. Notice it's not the absolute value inside the integral. I'm not saying that the integral of the difference between the two in absolute value, I'm saying that the difference of the integrals, maybe I should actually have written this clearly, as this is really x less than or equal to r rho1 minus rho2 x less than or equal to r. This is bounded by some constant times r to the 8 over 9, a b to the 4 over 9, and a to the 5. And I apologize for all these fractions, but somehow much of what I will do today will be gymnastics of fractions, and that's also why I have to calculate them from home, because otherwise I would have gotten it all wrong. Okay, so this is what I'm claiming. So let me prove this statement and let me copy this over. Let's remember that the A was the bound on the 5 first norm and the B was the bound with the difference of the Coulomb norm. Okay, so I'm going to prove it. So I'm actually going to choose a cutoff. So I will be integrating up to r. But I will choose a function that is 1 and then it goes down. This was not very nice. So the function that goes down and becomes, so this is r minus some little r, so theta is 1 for r for x. Minus r and theta of x is 0 for x bigger than or equal to r. Okay, and it's smooth and whatever, and the derivative here, the derivative there, the gradient is bounded by a constant r to the minus 1, this little one. Okay, so then I write rho1 minus rho2 x less than or equal to r. I write this as the integral theta times rho1 minus rho2 x less than or equal to r plus, here I don't have to write the r because theta was supported inside r, so here I can just leave the theta, but then I get 1, then I get 1 minus theta times rho1 minus rho2. Okay, let's look at the second term first. So let me call this 2 and let me call this 1. So let me estimate 2. Right, so I can use the triangle inequality and estimate each of these independently. So here I'm going to use that I will be estimating that this is less than or equal to x between r minus r and capital R, and then just rho1 plus rho2. So here I'm just taking the sum, I'm just doing a very bad estimate, and then I do another and compare it with rho5 first. So I'm getting integral rho1 5 thirds. So maybe I just use it as to go writing the norms. So I'll get rho1 5 thirds plus rho2 5 thirds. And then times the 2/5 norm of the little volume that I have from r minus r to r, but this is something I can estimate by r squared times little r. So that's the volume of the angles. so all in all, the term 2 is then less than or equal to, recall that this is what we call A, this we call A, and this is then r squared r, so this would become less than a constant times A, and then it was capital R to the 4/5 and little r. So this was 4/5 and little r to the 2/5. Right? This is what I get from that estimate. Okay, then I have to estimate 1, and recall that 1, this was the theta times rho 1 minus rho 2. Of course, this I can write instead going to Fourier transform, so I can write it like this, and let me put it there. And then this is equal, this is then bounded again by using Hilda by p squared theta hat of p squared to the 1/2. So maybe actually we put absolute values here. So this was actually an identity. This was equal to that, so the absolute value. And then this is also an absolute value, and now this is an inequality. And then you see that what you're getting now is the rho 1/2 minus rho 2/2. Well, let me write it as 1/2 actually. Rho 1 minus rho 2 of p squared over p squared. So in other words, it's a constant. It's a constant times the gradient of theta. If I write it in absolute value, I can write it as constant gradient theta absolute value L2, and then the Coulomb norm of rho 1 minus rho 2. Okay, and how big is the gradient theta squared? Well, recall that the theta this was bounded by, there was an r to the minus 1. So it's again, and that becomes, because of when I take the square root, it becomes r minus 1/2. And then it's actually the volume of the little annulus again, which is r times r squared, also to the 1/2 times what I call b before. And then what you find here is that I guess I made a mistake, because this was there was a square, so here there was no. This was just r to the minus 1, because that's the size of this quantity. Right? So all in all, this will give you a constant r minus f, and then r, and then. Okay, and now you have these two terms, this one and that one, and then you're just optimizing little r. And I can give you the answer for that. Little r should be some constant times r to the 2/9 b over a. B over a to the 10/9. And when you plug that in, you end up with having proved this estimate. So actually, let me take this estimate and let me now use it on the situation we have. So just to remind us what it is. Now I would like to use this for rho 1 being rho gamma and rho 2 being rho TF. And then I find that the integral x less than or equal to r, rho gamma minus rho TF, is less than or equal to a constant r to the 8 over 9. And then the b was the Coulomb norm. So this was z to the 7/6 times 1 minus eta, but I have to multiply now by 4/9. So it becomes 4 over 9, 7/6, 1 minus eta. That's what I get from the b. And the a was 7/3 to the power, well, I forgot, I better check here, what did I say? It was it was 7/5, right? Because it was 7/3 to the power 3/5. And so it was 7/5. So the a is then this becomes z to 7 over 9. Because it was 7. So that's what I forget the minus eta for a second. Right? So let's look at let's for a moment look at the z to the. Let's look at the z to the 4 times 7, that is 28. So that's not what I want to do. I want to do 14, right? So it's 14, because the 2 and the 4 cancel the thing down there, so I'm getting 14 over 27. And then I get 7/9. And this I can write as 21 over 27. So this is equal to z to the 35 over 27. Okay, imagine that I now choose z to be r to the, if I think of z being r minus 3, this is the type of estimate I would like to do. So let's just think for a second that z is like, that I'm choosing an r here, which is, so if r would be like z to the minus 1/3, right? That means that z is like r to the minus 3, right? And if I plug that in there, I would get, am I getting this right? I'm getting this number right. Yeah, right. So then I would get here that this would be r to the minus 35 over 9. If I put in the minus 3, and then r to the 8 over 9 times r to the minus 34 over 9 would be equal to r to the minus 27 over 9, which is indeed r to the minus 3. So if I chose a radius that was of order z minus 1/3, I would here get an estimate which would be r to the minus 3. But I did not use that, I actually have gained a little eta there. So because of this little eta, I'm actually able to choose r to be bigger than z to the minus 1/3 and still do better than r to the minus 3. So using this, so in fact, we get that for r less than or equal to, say, z minus 1, sorry, not much less, I just want to say, for r less than z to the minus 1/3, and even a little bit better than that, let me say, delta. I'm not going to keep track of how much I gain all the way. It's important, but I'm not going to keep track of it. Then we would actually arrive at, then we would get that the integral of rho gamma minus rho Tf for x less than or equal to r, this thing would be bounded by some constant r to the minus 3 to some 1 minus epsilon. So you have to play to get the delta and the epsilon. So this was just to prove that we get, i.e., we get star for a small range. And that's actually the best you can do if you were doing the real end. This same argument would work for the real end. But we want to do better now for Hartree Fock or reduced Hartree Fock. We want to extend the range of R's for which this holds. And the claim is now that we're going to do this in an iterative manner. Or rather, we will actually prove that assume I really have to keep it straight, so claim, assume that star, this is the thing we want to prove, right? This is actually this estimate, but that it holds up to some R, so assume star holds for R less than or equal to some R1 with R1 less than some R0, we'll say strictly less. I had this R0, I haven't told you what R0 is yet, it will come out of the proof. R0 is some quantity that would be independent of C. So I'm claiming that there is an R0, so that if I assume star holds for R less than or equal to R0 with R1 less than R0, then it holds for R less than or equal to R2 with R2 less than or equal to, I mean R2 bigger than R. So what I'm saying is that I claim that if I can prove star up to some R1, and if R1 has not gone beyond this R0, then I can actually choose it big. That means that there's nothing that will prevent me from proving the inequality star all the way past R. Okay, so let me explain how we will do that. And the idea is to again estimate the energy semi-classically, but now actually to split the energy in an inside and outside part. So the idea here is to split the atom in an inside part. So that's x less than or equal to R0, R1. R1 was the radius where I assumed that I know star. And I should emphasize that I do know star for very small r. So sort of the induction or iteration starts somewhere, and I'm saying it will not stop until I have gone past it. So the idea is to split the atom in an inside part x less than or equal to R and an outside part. Now this is a little bit technical, so a lot of estimates one has to do around the splitting, but so just morally, what you want to do is you want to write the gamma as and I call it again a theta minus gamma, theta minus plus theta plus gamma, gamma theta plus. I mean, this is not really correct. I mean, I cannot really write it like this. There will be some extra terms if I try to write like this, where I mean I have theta 1 minus theta 1 squared plus theta 2 squared equal to 1. But so I should maybe rather say that I want to replace the gamma by something like that. And I want to use that to try to estimate the energy. And I want to show that the energy of the full thing, so the reduced Hartree-Fock energy of gamma, is essentially equal to the reduced Hartree-Fock energy of gamma. So if I call this thing here gamma minus, and this thing here gamma plus, so this is essentially gamma minus plus, sorry, this is gamma minus, and then plus RHF of gamma plus But the gamma plus, the thing outside, it does not see the nuclear charge C, it sees only the screen nuclear charge. So here I'm trying to do that. So that's the whole point, that I can split like this, plus localization errors. And I was not careful in telling you where the theta minus and the theta plus were localizing exactly. I just want to point out one thing, that in localizing the kinetic energy, that's sort of where I have the main price to pay. Right? The fact that the theta minus, and this is something we actually discussed before when we talked about the proof Leibniz inequality, that if you look at you will have a point where you have to compare this to minus the Laplacian. You have to compare this directly to the minus the Laplacian, and this will be with an error. There will be an error here, but the error is like the gradient of theta minus squared plus gradient of theta plus squared. So this will be of order r minus 2 if I localize in a region of size minus 2. Right? So note that if theta minus theta plus localize in region, say R to R plus R or R to R minus R, something like that, then the localization error will be of order R minus 2. And then what will the total localization error be? The total kinetic energy localization error will be of order the trace of gamma times something like R minus 2. But remember that the trace of gamma, this has to be calculated on the support, restricted to the support of the, well actually it's important that it's on the support of this gradient theta plus minus, which is outside, in the region between say R and 2R. And this is where I actually know that, so this is R minus 2, trace of gamma in this region. But because I've assumed that I have this estimate star, I know that this thing here is actually bounded by R to the minus 3. Right? Because I know that it was close to what Thomas Fermi would be, and Thomas Fermi would be R minus 3, so it would be R minus 3 up to an error. So I can easily do an estimate R minus 3, so this would be R minus 2, R minus 3. Okay, so the localization error that I'm making in the kinetic energies of that order. But what am I actually expecting? What am I finding? I mean, what is it that I will try to estimate? The point is that I will not estimate this thing here. This is the energy close to the atom, and I have no way that I have a chance to estimate that. That's of order z to the 7th. I want to estimate this thing here, because here the problem depends only on u of r, and that will maybe allow me to estimate what gamma plus are, what gamma plus is, and then to find out how much mass I have in gamma plus. Right? So I expect that what I want to estimate is this E reduced half-reflow of nu of r. But I do expect that, I know that this is probably, it's a little bit different from the problem that I studied earlier on, because I'm not just estimating this quantity here, because I'm estimating it on a gamma plus that lives outside x equal to r. So I want to keep this in mind, that I'm restricting this to the part of the atom which is outside x equal to. So, but in any case, this is a nuclear charge of size nu of r, so I expect this to be nu of r to the minus 7 thirds. And this, remember, this was a constant, again, r to the minus 3 to the 7 thirds, So I'm fighting an energy which is r to the minus 7. I would like to understand the energy to order r to the minus 7. But then notice here that I have plenty of room. If I chose the little r to be the same as capital R, I would only get r to the minus 5. And after all, r is something small. And so r minus 5 is much, much smaller than r minus 7. It's small, but in a way that's independent. Notice z has disappeared in all these estimates. So, of course, I'm not going to choose r as big as capital R. I want to choose it smaller because there will also be, I will miss some mass when I look at the, separate the inside from the outside, so it would be important to choose r much smaller than capital R, but there's plenty of room up to the r to the minus 7. So, I'm simply going to, for now, ignore these localizations. They're simply small. Instead, all I have to do is to estimate this quantity. And this I can now do in exactly the same way as we did. So I just want to emphasize that we can safely ignore the localization. I mean, ignore us. I mean, yes, I should say we can easily estimate. It's probably a better way to write it as a mathematician. So I should say easily. Estimate the localization below. Right, and that leaves us with control limits. This E RHF mu of gamma plus with gamma plus supported outside x. I mean, supported outside meaning for x greater than equal to 1. Okay, so this is what I'll do. So we will do this again by a semi-classical lesson. And compare to a TF theory defined for x greater than 2r. Okay, so what we will be concluding, we will find, as before, that the rho, so let me now call it rho plus. So let me say, so rho plus is here the rho of gamma plus minus, and let me say rho TF plus. It's not the usual TF theory. It's a TF theory for the outside atom. I'm not comparing to the usual Thomas Fermi theory. I'm now comparing this outside problem, the thing that I have to estimate that. I'm comparing this with its own Thomas Fermi theory. So I will get this estimate here, that this thing is less than or equal to, so this is in the Coulomb norm. So it will be bounded by r to the minus 7, and I have to divide by 2, and then 1 minus, sorry, it was r minus, r minus 7, 1 over 2. And I can have the 1 minus 8. When I do the semi-classical process. This is before I have the Coulomb norm, so maybe I should do it with a square, maybe this is less confusing that I would have. I would get that this is less than r to the minus 7, 1 minus epsilon. This was, sorry, 1 minus eta. This was the lower order of the energy when I do the approximation. So this I'll find again. And I would also have that the rho plus 5/3 and the rho plus Tf 5/3, these are both less than r to the minus 7 to the 3. So I have those two estimates again, and I can use the lemma in exactly the same way, and I will get exactly the estimate I want. Right? So using the lemma again, we find that the integral of the rho plus of x, and this is now between r and some larger, so I should say, so r1. I was doing this all the way up to, here I should actually have said r1, because this was the region up until which, so maybe it would have been better to everywhere have talked about the r1. This was the point, the last point where I knew I still had the inequalities. And so I was going all the way up to r1, so it would have been better to write r1 here. So I'm localized also here when I say where I'm localized. I go as far as I can, so it's from r1 to r1 plus r. Because that was my assumption that I knew star all the way up to r. Okay, so here it's also r1, and here it's also r1. But that means that I can now go to a larger range. I can choose a r much bigger than r1. So r is now much more, I just say it, it's enough to say that it's bigger than r1. So that rho plus minus rho plus Tf is less than or equal to a constant, and then r to the minus 3, 1 minus 1 minus epsilon. Right? You have to be careful and check that you get the same constant as before, and that you get it. It doesn't matter if it's a smaller constant. It just doesn't have to be a constant that changes in the iteration. So you want to prove that you're getting this for r bigger than r1, and you get that. Okay? So that's very good. Except that that's not quite what we wanted, because we wanted to compare to rho Tf and not to this new rho plus Tf. Note that this rho plus Tf was defined for the new theory as an approximation to the new of r, right? Which was here actually this new of r was the reduced Hartree-Fock new of r. And so everywhere here I should have written the reduced Hartree-Fock new of r. Right? There's the new Tf of r, but there's also reduced Hartree-Fock. And this is the reduced Hartree-Fock. And this thing here is indeed the new reduced Hartree-Fock of r1. Because I started from r1 and I had an outside Thomas-Fermi problem. The outside Thomas-Fermi problem is again neutral, so it reproduces the charge that I have. Okay, but what I'd like to, so let me then try to actually estimate the new RHF to an R, which is bigger than R1. So recall that this was z minus the integral x less than or equal to R of the rho gamma. But this is of course the same as z minus the integral x less than or equal to R1 of rho gamma minus the integral between R1 and R of the rho gamma. And the first term, the these first two, that's the nu of what I call nu RHF of R1 minus this integral R1 less than or equal to x less than or equal to R rho gamma. Right? So let me take all of this over on the next slide and continue the estimate. Right, now I don't need all of this, so I'm just going to take this thing here. Move it up there. And I'll continue this. Because recall that the last term here, that's the one that I now have a good estimate on. This, that term is actually the same as the rho plus. This is actually equal to, and I'm here ignoring the different localization errors I may be doing. This is the integral of the rho plus from R1 less than or equal to x less than or equal to R. But that's the same as putting in this Thomas family theorem. The rho plus Tf with an error which is O of R to the minus 3, 1 minus epsilon. The R, the point here is the error is R and not R. Okay, but now recall that I can write this as the rho Tf from we had this new RHF. This was the integral of this rho Tf over the whole region. So I get this plus the error, and that's equal to, of course, the integral when x is bigger than or equal to R rho plus Tf plus O of rho R minus 3, 1 minus epsilon. Okay, so what did I achieve? Not much. I just rewrote it as being the integral of rho Tf outside. But now there is the miracle happening, that the rho plus Tf satisfies a Tf equation, Thomas family equation. And such equations have a universal asymptotic form. Which means that the integral when x is bigger than or equal to R of rho plus Tf, of the rho plus Tf is actually equal to the original Tf for x bigger than or equal to R with an error that's O of R to the minus 3, actually with a much better epsilon than the one I got from the energy estimate of that person. And that proves that nu RHF of R is equal to the integral of x bigger than or equal to R rho Tf plus O of R minus 3, 1 minus epsilon. But that is the same as z minus integral x less than or equal to R rho Tf plus O of R minus 3, 1 minus epsilon, which is nu Tf of R plus O of R minus 3, 1 minus R. And that's what I wanted to prove. That was the form star of the equation. Right? So I proved that if I knew it up to an R1, then I would actually be able to prove it up to an R, which is bigger than R1 and get the ISTA. Okay, so that proves the main result that I wanted to prove today. Maybe let me say a little bit about what does it have to do with the radius of atoms, and then maybe also say a little bit about what does it have to do with the ionization. So, I don't know why I guess this is already been erased now. Well, okay, I'll just go to the next slide. No, wait a minute, I'm just going to erase that slide. This is some problem with my question. Then I'll go back here and get the new slide. Keeps doing it. But whatever. I'll go to the next. Okay. So notice that what we have proved now is that so we have a good estimate. What I call nu of R, which was Z minus rho gamma of x, dx for x less than or equal to R, up to R less than or equal to some R not independent of C. Now let's look at the neutral. Let us look at the neutral case. That integral rho gamma. I know that there is a minimizer in that case when rho gamma is right. Then nu of R is actually the same as the integral when x is bigger than or equal to R rho gamma of x. And recall that the condition for being the radius out to the last n electron was that this thing here was n. Or put differently, that the nu of R, if I calculate nu, and I should maybe be careful and always call this nu of RHF, right? So I know that nu of RHF evaluated at RHF of m, and that was the radius out to the last m electrons. This is actually, it was defined in this way, right? That the integral outside, this was equal to m, right? But now I know that I have a very good expression for this quantity. Right? I know we know that this nu RHF of R behaves like some Thomas Fermi, the same constant as you would get in Thomas Fermi, times R to the minus 3, or R small. But independent, still independently of C. Right? So I can take can think of taking the limit when z goes to infinity. And if you compare with what I was claiming I wanted to prove, this was this statement here, that if you calculate the RHF, the radius to the last n electrons, then it indeed goes like n to the minus 1/3 with the constant that you get from the Thomas Fermi theory, and that is exactly what I have argued from this statement, because we would then have that there is the relation that m goes like r to the minus. Okay, so that proves that statement. So we get the claim asymptotic for this RHFZ of m for large. M that it goes like the TF quantity, and this is actually the infinite Tn quantity times n to the minus 1/3. So that when I take it to the minus 1/3 power, I would get n. Okay. So the last thing I wanted to mention was the was ionization. So how to prove? So maybe we can do it like that. This keeps coming up. Finally, let us prove. Well, let's make it that if gamma is a minimizer for easy RHF, then trace of gamma is less than or equal to plus a constant independently of z. Okay, so what you do is, the idea is that we know that this new, the screen charge at the radius r, so that was z minus integral rho gamma x less than or equal to r, that this would be like r to the it doesn't really matter if r, we know that if r is independent of z, then this thing here is over 1. Right? It was really r to the some constant times r to the minus 3, but that's really something which is over 1 in z. Right? And now what I do, I again do an inside-outside. But we use now and use the least method to get a bound R, the integral of gamma for x bigger than or equal to R. This is the number of electrons you can have outside. And the lead method tells us, well, that this is 2 times the charge, which is nu RHF of R. Now it doesn't want to do it. Times 2 plus 1. Doesn't matter, this is over 1. Right? So all in all, we see that the integral, so we have this already, right? So we see that the integral of x, the integral of rho gamma that's equal to the integral x less than or equal to r rho gamma plus the integral x bigger than or equal to r rho gamma. The first thing we can see from here that the difference to z is order 1. So this is equal to z plus order 1 plus order 1. So it's bounded by z plus. Now the same argument would have worked if we had done it at the first step also. And that's actually a way to prove that you have asymptotic ionization for the quantum model. But here for reduced Hartree-Fock, we can actually prove Z plus. So what I talked about today, you will find in 2 papers by me. So one is in Inventiones in 1991. It's ancient. That's the ionization in RHF. And then quite a bit later, I proved also for Hartree-Fock, so this was in Amos 2003. It's not that it took me 12 years to prove it, it took me 5 years to prove it and 7 years to write it. So this was ionization in the Hartree-Fock. So thanks a lot for your attention. It's 10:45, so I guess it's time to...
Thanks very much, Jan-Philipp, for this very nice series of lectures. Any questions, comments? Now you have seen the whole scope of these 4 lectures, so every question is allowed about everything. Yeah, Robert. Most.
Maybe let me start. Thank you, Jan-Philipp. So one question about what you explained today. You were sort of explaining first how to get control on the number of electrons up to a certain radius, and the first step is basically just z to the minus a third, or something slightly bigger, so to say the Thomas Fermi scale. And then I think there's an iteration, right, to sort of get to larger and larger scales. What stops it at the end? So I think it wasn't very clear, why is the R0 at the end order 1, right? So
Right, that's a good point. Because I want to do a semi-classical approximation. Right? So when I want to calculate the energy for the outside part, I compare with the Thomas Fermi theory. And this is a semi-classical approximation. And for that, I need some small parameter. And the small parameter is, or small or large parameter. And the large parameter is the nuclear charge of the outside. So only as long as the nuclear charge of the outside button is large enough, am I allowed to do such an estimate. So that's why. So I need this nu of r. The nu of r is the nuclear charge. That was r to the minus 3. So I need the r minus 3 to be large enough for all of these estimates to be of leading order. Now, I mean, in some sense, at some point, what we will get is that this difference between these integrals will be a constant, will no longer decay like r to the minus 3, 1 minus epsilon. And that's simply because you can still do all the estimates, but you'll get lots of estimates which will be of order 1 when the nu of r becomes of order 1, and then you have no way of sort of singling out the leading term.
Thank you. Maybe I can ask a second question right away, but then I give the mic back to you. So in this general procedure that you explained today, what is the main obstacle to try to generalize this to the actual full quantum problem?
That's when I split it in an inside and an outside. So what I did here was I followed the iteration in this nu of r, the screen nuclear charge. The outside problem in reduced Hartree-Fock, it's very easy to see that what the atom sees outside is only the screen charge from the inside. In Hartree-Fock, it's actually slightly more complicated. You cannot say that it's really only the charge. It's rather the potential generated by the charge. Because when you have when you have reduced Hartree Fock, everything is spherically symmetric, and the potential created by the charge inside is just given by the charges. In Hartree Fock, it's not spherically symmetric, and therefore, if you cannot just follow the charge, you have to follow how the potential from the inside is seen from the outside. But that can still be done. That was this amnesty. Now, if you do a quantum model, well, then you have correlations, you have entanglement of the inside and the outside. So I have not been able, and it's probably because I'm not seeing it, I think it should work, but I have not been able to split the inside and the outside. And get an inside problem that I can control. And the thing is that you can do certain things, you can probably improve some ionization estimates, but remember that this inside atom, you're going to the limit where Z goes to infinity. So you should think of having infinitely many electrons. So very close to the nucleus, you have infinitely many electrons. You have to control that these infinitely many electrons do not correlate in strange ways with what you're getting outside. And one way you might want to control it is to say, well, they are so deep down in this Fermi sea that they can't move. But that requires some estimate on how many electrons are close to the Fermi sea, right? I mean, what are these sort of the valence electrons? And maybe you have actually an order of Z to the 1/3 of those, and then even Z to the, I mean, even a Z to the epsilon is going to kill you, because you need an estimate that the inside affects the outside in a way that's independent.
Thanks.
Thanks. Any other question, maybe more from the students? For the students, everything was clear. It's only for Robert. It was quite clear. So just look around. Well, then, young Philip, then everything was very clear apparently. So thanks very much once more for the very
I
nice.
encourage you to go to August's lecture tomorrow and get the last chapter of this book. Sorry, that's it.
I think it's not tomorrow, it is this afternoon, so the last of
Oh,
the
really?
day.
I thought it was Friday. Ah,
No, it's today.
okay. But anyway, I'm still encouraging you if you want to go.
Sure, of course, there you go. Okay, so thanks very much once more, and give a big applause for young Philip. Okay, thanks so much, and as usual we have a break now, and we will reconvene in 25 minutes for the coffee outside.
Đây là sinh viên cầm này của tôi.